In problem 11.29, you are asked to calculate the effective value of the current waveform that you see depicted on your screen and the average power delivered by that current waveform to a 12 ohm load. So, in this problem, what we will begin by doing is finding a mathematical model for I at any given time t. This, of course, is a piecewise function, and each of those pieces is linear. So, as you can see here, I of t is equal to 6t starting at 0 and going up through 5. And then we have a line that has a slope of negative 6, and so we put in negative 6t, and you can solve for the intercept here just by plugging in this point right here, 5 and 30. And so that will tell you that you need a plus 60 in there for the interval between 5 and 15. Once you get beyond here, now we're back to a slope of positive 6, so you get 6t, and again, using either this point or the point on the end, you can find the intercept just using basic Algebra 1 principles, and then yet again, we have this down here. Now, why are we finding I of t? Well, if you remember, the formula for the effective value is going to be the square root of 1 over t, so one entire period, times the integral from 0 through t of, in this case, I squared dt. So now we have I, now we want to find I squared. So all we need to do is just take each of these individual values for I of t and square them. So within the same interval, we just take 6t, square that, that's the easy one, that's 36t squared. Then we're going to square the quantity negative 6t plus 60, and so that works out to what you see here. Take the quantity 6t minus 120 and square it, and the quantity negative 6t plus 180 and square it. Now, if you look back at this function, one full period would go from, in this case, 0 all the way up through 20. This is not exactly a sinusoid, but you see this triangle wave, and one full period, it looks like it's going to be a repeating pattern. So we want to find the integral over 0 through 20 of this function. And so here is our effective value. The effective current is going to equal the square root of 1 over the period, so the period is going to be 20 seconds. The integral from 0 to 5, so this is our I squared from 0 to 5. This is our I squared from 5 to 15, and this is our I squared from 15 to 20. So we're just integrating all of those. Now, if we go on down, what you're going to notice is you're taking an integral of 36t squared over the entire interval. So I took the liberty of combining that into just basically pulling out the integral of 36t squared dt and making that over the entire interval from 0 through 20. So that's what you see here is the 12t cubed. We're going to evaluate that from 0 to 20. This is coming in from your 36 t squared, that's coming in there. And so here, this is coming in from your negative 720t. That works out to negative 360t squared, evaluated from 5 to 15. The 3600, you get 3600t evaluated from 5 to 15. Then your minus 1440t, that goes to minus 720t squared, evaluated from 15 to 20. And then you have a 14400, and so that becomes 14,400t evaluated from 15 to 20. If you go ahead and evaluate those on out, so I show my work here, just plugging in 20 minus 0, and then I just plugged all this in all the rest of the way down, and then add all these values up, divide by 20, what you end up with is the square root of 300. So if you go ahead and plug that into your calculator, you get about 17.321 amps. So what that means is if you were to stimulate a load with a current source that had this particular shape current, a triangle wave shape of current, then you would have effectively delivered the same amount of power as though you had a current source that was a DC steady current source of 17.321 amps. Now, the last part of the question is what is the effective power delivered to a 12 ohm load. So all you need to do is take the effective current, square it, and multiply it by 12. So since it's the square root of 300, we just simply square root of 300, get 300 multiplied by 12. That works out to 3,600 watts, or 3.6 kilowatts.